Hello, and welcome to my talk, ETR Completeness, or Framework for ETR Completeness of Packing Problems. My name is Tillmann Miltzow, or just Till, and I'm from Utrecht University. And those are my collaborators, Mikkel Abrahamsen from Copenhagen and Nadja from Berlin Free University. So Nadja was called Nadja Scharf at the beginning of the project, and during the project she married, and now she's called Nadja Seiferth. And that is maybe also part of the inspirational story for what we're doing in this talk. So there's this fictitious character called Paul. Let me introduce Paul to you. So Paul, he likes doing photography, he likes to play badminton, and he likes to read books in his spare time. But more importantly, Paul recently got married to Nadja. And so since they got married, obviously they want to go on their honeymoon. Okay, so this motivation was done before Corona. So they're going on their honeymoon, and they're going on a hiking trip. So maybe you could do this in Corona. Anyway. So what they take with them during their honeymoon is a bottle of water, some sandwiches, a sleeping bag, a tent, a blender, of course you want to have your smoothie in the morning, and a shower. The usual stuff to take with you on a hiking trip. Problem is, they have only one bag, and they want to fit everything of their stuff into the bag. And this is somehow the one motivation you can think of for what we are studying in this talk, namely putting stuff into other stuff, also called packing. And so some people are more interested in more serious applications. So let me thank Miltzow for providing us with these real-world cuttings and nestings coming from industrial applications. And here on the top we can see that we fit. We have like a large piece of fabric, and we want to cut out pieces such that we can use those pieces then in order to make our t-shirt or whatever. And here we're not allowed to rotate this because the fabric has a certain alignment. But we see, for instance, that there's curvature in the fabric, and we want to place everything so as to waste as little fabric as possible, right? To save resources. It's good for economic point of view, but also for an ecological point of view. At the bottom, you see another example of a packing problem, which is actually happening in industry. So you have here a patch of leather, and you want to produce some leather items. Part of that leather may not be usable for that. And of course, you want to use as much of the leather as possible. And then here you may be allowed to use rotation because maybe the orientation of the leather is not relevant. And again, you want to waste as little leather as possible, so you need to place stuff in a as clever as possible way. And so what you can see from these examples, in real life packings, they are not just about translations. Rotations are actually very relevant for packings. You may not just have to encounter rectangular containers, but also all types of weirdly shaped containers. And a lot of the pieces that you want to cut out or that you want to pack, depending on the way you want to look at it, are not polygonal, but they have curved boundary often. And they also may not be convex. Okay. So this brings us to an overview of different types of packing problems. So we may allow different types of moving operations either. So here we have rotations and translations. We have different types of pieces that we want to pack between unit squares, the most simple ones, and arbitrarily shaped plane. We have also different types of containers. Here we just consider 4 different types of containers. And then we have like this complexity landscape. And the complexity landscape is kind of very homogeneous. It just says, well, we know about all of these problems that they're NP-hard. And our contribution is that these problems are, a large set of them are harder than NP-hard. They're actually ETR complete. And ETR complete stands for Existential Theory of the Reals. I'm gonna explain in more detail that complexity class, but for now it's just more difficult than NP. And in order to give you a flavor of that inherent difficulty, I want to take a closer look together with you at placing unit squares inside a larger square along rotations. Okay, so container is a square, pieces are unit squares, and the simplest case is that is non-trivial is just 5 objects. And here, this is the optimal solution, and it's maybe not so spectacular, but there's a subtlety here, namely that already in order to describe that solution, you need algebraic numbers. You cannot do just with rational numbers. Okay, so but a more disturbing example is, or fascinating, depending on what side of the story you're on, is if you have 11 unit squares and we want to find a packing for that. So here I described you one packing inside a square, but we don't know if it would not be possible to fit those objects in a very different way in a smaller square. So this is the best known packing that we have, but we don't know if there's a better one. And you see that these packings very quickly can become very complicated. Very complicated. And also irrational numbers can come in, and arbitrary types of rotation in a kind of unexpected way. And it's disturbing that we don't know the optimal solution here. Okay, so going back to the big picture, so that's the first set of results that we have. And I said it's a framework, so we show all of those results in like a similar way, and there are small adaptations only for each of those proofs. Then if we only allow translations, then we know actually that a big subset of those problems are contained in NP. And this goes as follows. So we want to know we want to describe the placement of all the pieces. So for each vertex of a piece and each edge of a different piece, we can guess whether the vertex is on that side of the edge or on the other side, like above or below. And when we guess this enables us to describe an LP. We can solve the LP in polynomial time. So bottom line, what we get is we get a description with rationals describing an optimal placement, and the description complexity of these rational numbers is small. So that shows us that all of those problems where we only allow translations and all the objects are polygonal are solvable in NP time. But when we allow more difficult types of containers or more difficult types of objects, then the problem becomes ETR complete. And for certain problems, we don't know what the correct answer is. Okay, so now that you know the results, you're like, okay, but what is this complexity class ETR? So let me define it to you, and I'm going to use that you already know about the complexity class NP. So one way to define NP is like, okay, you look into your crystal ball and you guess some bits, a polynomial number of them, and then you check that these bits describe you a yes instance using the word RAM model of computation. And now that I want you to think about ETR in exactly the same way. So you look in your crystal ball, but now you guess not bits, but real numbers. Okay, crystal ball, real numbers. And then you need to check whether these real numbers are working out, like describing you a positive result using the real RAM. So the real RAM is like the same as the word RAM, but you're also allowed to do computations with real numbers. And that is a description of the complexity class, or that gives you a definition of the complexity class ETR. So instead of checking, instead of guessing integers, we guess real numbers, and instead of checking them on a word RAM, we check them on the real RAM, which allows doing computation with real numbers. Okay, so now that you know the definition, let me give you a placement in relation to other complexity classes. So since the real RAM is more powerful than the word RAM, we have that NP is trivially contained in the complexity class ETR. And Kenny came up with a very sophisticated algorithm, I think already in the 80s, to show that ETR can also be solved in with polynomial space. So we have a containment in the complexity class P space. Other people have then refined the algorithm from Kenny. So that's kind of a well-established, but also a very sophisticated result, which was a breakthrough back in the day, and I think it still deserves recognition as one of the outstanding results. Okay, now I want to give you a few example problems so that you see this is not a made-up theoretical complexity class, but it contains many algorithmic problems that we care about, and actually many of those problems belong to computational geometry. So one of those problems is you've given a graph and you try to draw that graph in the plane with as few crossings as possible, so a vertex represented by a point and an edge represented by a line segment. Another problem is recognition of disk intersection graphs. So I give you a graph and then I ask you to represent it using disks. Can you do it? Can you not do it? So you would represent in the following way. For every vertex, you get a disk. And if you have two vertices which are adjacent, then the two disks should overlap. Okay, so that would be also an ETR complete problem. And surprisingly, it's already ETR hard for unit disks. So that's a very non-intuitive, because unit disks seem like a really easy object to work with, but they're not. For computational geometry, a very important problem is recognition of pseudo-line arrangement. So you may know what a line arrangement is. In a line arrangement, you give a bunch of lines, and then just you look at the combinatorial structure because you get faces and vertices. And with a pseudo-line arrangement, you just have curves, and you try to get the same arrangement using straight lines. And another famous problem in computational geometry is the so-called art gallery problem. Here we are given a simple polygon in the plane, where it represents like our art gallery, and we try to guard all the art. So we place guards in the gallery, and we want to place as few as possible. So we have some upper bound of guards that we're allowed to use. And then they are supposed to guard the gallery, and 2 points guard each other, or 1 point is guarding another point, if the line segments between them is fully contained inside the polygon. It's a little bit like what we usually just assume as normal vision. So these are kind of famous problems in computational geometry. And yeah, so problems in there are more problems in computational geometry which turn out to be ETR complete. So I hope this gives you a flavor of what types of problems you could expect to be ETR complete. Okay, so why should I care about ETR completeness? We already know NP hardness of all the packing problems, you could think. But somehow for a lot of NP hard problems, we can find optimal solutions fast. They're like, we can't find in polynomial time, but in practice we can do it fast. For ETR complete problems, usually we cannot do that, or there are much harsher limitations to this. So and the reason is that we had a lot of tools like integer programming, approximation, local search, and all these tools, they stopped working for ETR complete problems. Already often just exhaustive search, like the trivial algorithm, just try everything, doesn't work for ETR because there's an infinite number of possibilities. So really it's much harder to solve these types of problems, and that's why it's interesting to figure out that a problem is ETR complete. Okay, so now I want to show you some of the key ideas on how we show this ETR completeness. I will not go into all of them because many of them are maybe more standard, or they take a lot of setup to describe them. So I only describe some of the key conceptual ideas, which may be very different to other types of reductions that you have seen. Okay, at first, our reduction goes in 2 steps. So first we take the general ETR type of problems, and then we reduce them first to a very simplified type of problem, which we call ETR-inf. And then from ETR-inf, we go to packing. And this ETR-inf is, or in general, I think for many types of reductions, we have these intermediate problems which have like some additional properties that we're going to use. You see this often also for p-space hardness, APX hardness reductions. So what is ETR-inf? So here, because in packing, all our objects are in a bounded range, also we need our variables to be in some bounded range. So this will be actually between 1/2 and 2. And to be more precise, we will also have the property that we get this promise that if there's a solution at all for every variable, we get this little interval in which a solution, it's very small interval in which it will be contained. Additionally, we don't have to show all types of things that can come up in ETR. Not all types of operations, but only 2 of them. One is addition and the other is inversion. So that makes our life also considerably easier. Okay, so now how to encode one variable. So for one variable, we use one piece, and the value of the variable is the position of the piece. So here we have a green piece, corresponds to this variable x, and then we have different positions of that piece, and that would correspond, for different values that piece is going to encode. Okay, and we may have more than one piece per variable, but then we will make sure that all these pieces will consistently be placed so that they encode the same value. Okay, then another feature is, so we have to encode addition. And so this is like a simplified way of displaying the addition gadget. And here we have only one inequality. And what you can see is that if I push x, right, I also have to push z. And if I push y in the other direction, then z can also go further to the left. Okay, and so you then also can do the other type of inequality. And the inversion gadgets, they're looking more complicated, and it was a lot of work to try to figure them out. But I think they're not very suitable to be described in a talk. And they're kind of a similar flavor that you have, some geometric constructions and certain movements of some variable, of course, certain movements of some other variables, and then you have some dependencies in some way. Okay, so there is a fundamental problem with our reduction. In general, if you have a reduction for packing problems, namely, you give in the end the end of the reduction going to be a container and some pieces. But really, what we want is we want them to be placed in a specific way, but in a somewhat canonical way. But they could be placed in an arbitrary way, right? And then we have this encoding of this piece means this variable, it just goes away. So in order to have that possible way of encoding, we need to make sure that the pieces are where we want them to be. And there are 2 ideas to do that. One which we are not going to use, but which is very instructional to think about. And then one we're going to use, but is more sophisticated. And the first one is just like a puzzling, right? You have your puzzles, and one piece only fits at one position. And if you have like, oh, these puzzles, these tiles are both blue, oh, but they don't fit. So you can't place them next to each other. And that's exactly the idea here. So we have maybe part of the boundary shaped in a very specific way. And then we place a piece there, and then only that piece can fit there. And you can still move it up and down, so we have some slack, but another piece could not fit. And then you can also do this with pairs of pieces and so on and so forth. But there's a big downside, because all these pieces, in order to do this, must be non-convex. So now I want to show you the idea of a different technique, which we call fingerprinting, which is going to achieve the same, but with convex pieces, but it's going to be much more elaborate, and it's like 30 pages of proof that this is going to work. But then the idea is very simple. So imagine the container has almost exactly the same size as the same area, as the total area of all the pieces. okay? Then let's say you have one corner of the container and you want a specific piece to fit exactly there. What happens is that all the angles are sufficiently different so that like there is a piece that fits exactly, but then another piece, what happens is that if it either has a smaller angle and then there's this little empty space that you can see there, and that empty space is so large that it's larger than that difference that I described on the top, or that a piece has a too large angle, but then again there will be this empty space. And so because of this area bound, we know that we can have no empty space there. Now it sounds kind of easy, but what makes this really hard is, so this forces us for all the variables to have a teeny tiny range. It's like n to the minus 300 if I remember correctly. And also we still have to allow some movement, so that we need to have, right? It also makes the construction of all our gadgets very difficult, because at no place we should have any slack, and we need to have the unit angle at every piece, and it's easy for boundary, but then you iterate this and you don't really know how we're looking like. So this just gives you an idea on what makes this finger techniques very tedious and difficult to prove if you want to really make it precise. Although the key idea, I hope, is relatively simple and straightforward. Okay, and the last thing that I want to show you is, so now we have this weird type of container, but what is really nice, we can also show hardness if the container is just a square, which is a kind of simplest container you could think of. And what we do there is we just fill the rest in a unique way, so that only the little previous container remains unfilled, and so then all the remaining pieces have to fit in there. And what happens is we use again the fingerprinting technique, and we use that the blue, green, and turquoise pieces fit inside the square in a unique way. So you could push the orange piece in the inside, but you couldn't make any use of it, so we know they have to be pushed to the outside. Okay, I know this is kind of hand-wavy, but you could imagine that these blue pieces could really not fit in a different way. And of course we show this in a very rigorous way in the paper. Okay, that was it. Let me mention again my collaborators, Mikkel Abrahamsen and Nadja Seiferth. Thank you for attention. Please also come to the live video. If you're interested, also please come to the poster session. And yeah, thank you for your attention.